critical clearing angle. In the equal area criteria, we see that for any given initial load, there is a critical clearing angle. If the actual clearing angle, if it is greater than the critical value, the system is unstable. Otherwise, if you are clearing the fault less than the critical clearing angle, then otherwise it is stable. Therefore, the area A1, area A is depending upon at what particular time you are clearing the fault. If you are clearing the fault beyond delta C, in that case the A1 is increasing, however A2 is decreasing. Then the area is A1 is not equal to A2. The system is unstable. That is the point corresponding to the clearing time such that A1 is equal to A2. Beyond that the A1 is not equal to A2. But however, when you are clearing the fault less than the critical clearing angle, there A1 is equal to the A2 you are getting. As the A1 increases, A2 is also increases when you are clearing the fault less than critical clearing angle. But at critical clearing angle, where just A1 is equal to A2. Beyond that, A1 is not equal to A2. Therefore, the A1 is depending upon the time taken to clear the fault. If there is a delay in the clearing the angle, the delta C is increasing. That is, delta C is increasing. Likewise, the area A1 is also increases. But the equal area requires that A2 has also to be increased. However, the A2 is decreasing, therefore the system is losing its synchronism. Therefore, you have to determine at what particular angle you have to maximum angle you have to clear the fault so that the system remains stable. Beyond that value, the system is unstable. So, we now proceed to determine the value of critical clearing angle for any given load condition. Just I am here drawing the power angle curve for a system which is the generator is connected to infinite bus. I will draw here three sets of curves, power angle curves. One is curve A, which is meant for pre-fault condition. Okay, before the fault occurs on the system, this is a power angle characteristics where the reactance is less. Therefore, we have got a maximum power we are getting here. This is pre-fault condition. When the fault occurs on the system, then the reactance of the system increases so that the power angle curve is reduces from A to B. That we'll see. But before the fault occurs, the system is operating at point A, that is corresponding to A. Our angle is delta naught and the mechanical power input is PS. Now suddenly there is a fault occurs, then what happens? That is a power angle curve is shifting from A to B now because the reactance is increased. Therefore, my operating point which is operating at A, because of the fault is occurring, then the operating point will shift from A to F. Then the operating point will move along the curve B. Then after some time I am clearing the fault and the power angle curve is shifting from B to C. That is, the reactance is little bit decreased. Then it is shifting to the curve C. Therefore, what happens here? At this particular point I am clearing the fault. That is, previously it is operating at A. Then when there is a fault is occurring, then the operating point is shifting from A to F. Then it is moving towards the G. At the point G, the fault is cleared. then the operating point is shifting from Z to H. That is, it is shifting to Z to H. That is, you can see the sequence of events what happened here. Before the fault, operating point is A. Then when the fault is occurring, then it is shifting to F. When the fault is not cleared, then the operating point is moving along this. And this at this particular point, the fault is cleared, then the operating point is shifting to H. Then there is a, because of the damping torque, the system, then H has to be moved to the swing of the angle towards the B. Therefore, we are getting the two areas here, that is the area A1 which is the acceleration area, whereas the B is the deceleration area for the generator. That is, the system is stable where A1 is equal to E2. If you are making any attempt, if you are clearing the fault somewhere here, then A1 is increasing, however A2 is decreased. In that case, A1 is not equal to A2, then the system is losing its synchronous cycle. It is a maximum angle at which you are clearing the fault. At that instant of time, just A1 is equal to the A2. Okay. With this, we'll see what is the value of this particular angle. At what maximum value of angle delta you can clear the fault so that the system remains stable. There are three power angle curves I shown here, A, B, C, that is pre-fault, during the fault and the post-fault condition. That is given by, one is before the fault, that is Pm sin delta, whereas during the fault the reactance is the increase because of the Pm is reducing here. This is a Pm of the healthy condition from here to here, whereas the Pm during the fault is this much. Therefore, that is represented in the fraction R1 P1. That is, it is reducing from R1 times P1. That is, a Pm is the maximum power transfer during the healthy condition. That is EV by X during the healthy condition. Similarly, as shown here, there is a third curve, that is after the fault is cleared, then it is given by R2PM. That is, R2PM is greater than the R1PM, however it is less than PM. That is, the R2 times PM sin delta will be the equation for after the fault is cleared. Now, for the tangent stability limit, the two areas A1 is equal to area, A1 is equal to A2, that is A1 should be is equal to A2, or equivalently the area under the curve ABCD. I will show you here the area under the curve ABCD. What is that? It is ABCD. What is this curve? It is the power under the mechanical power, that is PS. That is, the operating point is A, then ultimately it is shifting to lastly at point E, then what is the maximum change in the power from A to B, that is it is ABCD. That is, the area under curve ABCD in a rectangle should be equal to the area under the curve DFGFC. What is that? That we'll see here. That is, you can see here. Previously it is operating at this point, that is under healthy condition. Then the operating point is shifting to F. Then the operating point is shifting from F to here, F to G here. It is at the point Z here. Then from Z to it is shifting to H. Then H to B it is moving and it is C. That is, area is D F G H B C. That is, I am showing, that is under curve here. You can look into here. That is the area under curve D F G H B and C. That is a mechanical area must be equal to this electrical area during the healthy condition to fault condition, then the after fault condition. This is how that is the electrical power is shifting from A to F, F to G, G to H, H to B, B to C. This is the electrical power. This electrical power should be equal to the mechanical power of ABCD. ABCD. Then the system is the stable. That is how we have to equate the area A1 and A2, or this area under the mechanical curve is equal to the area under the electrical curve. Okay. Just I am making here, I will write in the form of the equation here. How I am writing here? Just you can see here. This is the first area, that is ABCD. It is the area under the mechanical power, that is ABCD. That is ABCD. How we are writing that? It is a PS into dm minus d naught. That is a height as PS, width is it is dm minus d naught. You can see here. This is the dm minus d naught into the PS. That is what I shown here previously. Okay. Next, in the right hand side, we need the area under this curve. Area under FGD, this area. That is, the equation of this curve is R1 PM sin delta. When the operating point is shifting from A to F, the power angle equation is now it is R1 PM sin delta. Then what is it is moving from F to C. It is moving from delta naught to delta C. Therefore, area under FG is nothing but it is integration of R1 PM sin delta d delta between the limit delta C to delta naught. That is delta naught to delta naught. It is R1 PM sin delta naught. The same thing I marked here. This area what you are interested. Therefore, you have to take the integration of this curve between the limit dc to d naught. Then the another area what we are interested is this area under this curve, that is this curve. Means the operating point is shifting from here to here. Operating point is shifting from Z to H. Now when it is shifting to H, the power angle curve equation is determined by R2 PM sin delta. Then it is changing from angle delta C to delta M between, that is why what you have to take the integration of the R2 PM sin delta d delta between the limit delta M to delta C, delta M to delta C, that is R2 PM. Then just you have to integrate this. Sin delta is minus cos delta. Put the upper limit and the lower limit here. Then what we are getting? It is R1 PM is the constant. Then actually we are getting cos delta C minus cos delta naught. But sin delta integration is minus. Therefore, what I am getting is cos delta naught minus cos delta C is if we are putting the upper and lower limit. Similarly, the integration of this sin delta is also minus cos delta. Put the upper and lower limit. Then the R2 PM is the constant. Then cos delta C minus cos delta M, what I am getting here. Then also I know that the PS, that is PS is nothing but at operating point A. Operating point A is nothing but it is PM sin delta naught. Operating point A is nothing but PM sin delta naught. Just I am substituting that value in this. That is PS is equal to PM sin delta, because at point A, if we are taking electrical power output is PM sin delta naught, because it is the angle is delta naught. This PM is EV by X, EV by X, EV by X. Now substituting this PM sin delta naught in this equation, what I am getting is delta M minus delta naught PM sin delta naught is equal to, the right hand side is the same, I am keeping as it is R1 Pm cos delta C minus cos delta C, R2 Pm cos delta C minus cos delta M. Just you have to look into here, you have got the cos delta C, it is appearing twice. One is R1 Pm cos delta C with a minus sign, and R2 Pm cos delta C, it is opposed to here. Therefore, if you are taking the grouping of this, then what I am getting here is, it is R1 Pm I am keeping as it is. Now in the second case, what I am doing, I am taking cos delta common from this term and this term. What I am getting here, cos delta is R2 cos delta C, R2 minus R1. Then the remaining term what I am getting is R1 cos delta naught and minus R cos delta M. Now I have got only cos delta C. Therefore, what I am doing here is, I am taking cos delta C, I am keeping this in one side, then the rest of the terms I am transferring to the other side. Then cos delta C can be, you are getting as delta M minus delta naught sin delta. Then this is minus R1 cos delta naught and is plus R2 cos delta M. Plus R2 cos delta M divided by R2 minus R1 divided by R2 minus R. Then how to find out the value of delta M? The value of the delta M can be calculated. You can look into here at this particular point A, that is equal to PS, that is equal to PS also is equal to Pm sin delta naught, that is corresponding to point A. That is equal to, you can see the curve C here, that is a point B. At point B, what is your output? The output is R2Pm sin delta M. You have to, it is following the curve C. In the delta corresponding to P, the delta is delta M, that is R2Pm sin delta M. The same thing I am putting here, R2Pm sin delta M. That is equal to R2Pm sin pi minus delta M. It is total angle pi, then that can also be expressed as pi minus delta M. Then if you are equating the first term and this term, then both sides Pm get cancelled. Then what I am getting here is sin delta naught is equal to R2 sin pi delta M. Or if you are interested in the value of the delta M, then delta M should be is equal to pi minus sin inverse of sin delta naught by R2. Just you have to make the simplification of this. Make the simplification of this so that you are getting the value of delta M. The delta M is pi minus sin inverse of sin delta naught by R2, and delta naught you are getting from Pm, that is operating point A, that is Pm sin delta naught. So that you know the value of delta naught, we know the value of delta M you are calculated here. Then R2 and R1 also the given quantities, so that you can find out what is the critical clearing angle, so that you should not go beyond this critical clearing angle, otherwise the system is going to the unstable condition.